So lactic acid was CH3CHOH COOH, only one asymmetric carbon. Tartaric acid is having two asymmetric carbons. It is having the formula COOH HOH H. This is the formula of tartaric acid. Now let us look at the possibilities in how many ways you can draw this molecule. How many ways we can draw this molecule? You can just try by yourself. Let us take the mirror image of this. That's the first way you can COOH, OH, H, OH, H, and COOH. See, this is the mirror image of this molecule. So what should be the relationship between these two? This is supposed to be enantiomer. Enantiomers. Okay, now let me tell you, is this form erythro or trio? Erythro or trio. How do you know whether something is erythro or trio? You take the first two carbons, first two asymmetric carbons, this and this, and see whether the substituents are on the same side or opposite side. So here the OH group is on the same side. For the first two carbons only. Yeah, here you will have only two carbons which are asymmetric. So here it is on the same side, it is called erythro. This is also erythro. Now let us draw the trio forms. COH, this is trio. And now one more, the last one. The image of this. See that. Okay, these two are mirror images. So these two you can consider as enantiomers. Okay, then you can see here there are two asymmetric carbons. This is one asymmetric carbon, this is another asymmetric carbon. So the formula is number of 2 power n, where n is the number of asymmetric carbon. So there are 4 possible structures. So these two are enantiomers, these two are enantiomers. And what is the relationship between this and this? As well as this and this. They are diastereomers. So these two are diastereomers, these two are diastereomers, and these two are diastereomers. So diastereomers are non-superimposable, non-mirror images. Remember that. They are not mirror images. Diastereomers will not be mirror images of each other. Okay. So we have two sets of enantiomers and two sets of diastereomers. But let us look at these two molecules. We'll go deeper into these molecules. See here. OH. If you keep, see, there is a symmetric element for this molecule. Even though it is containing two carbons, which are chiral, so it contains two chiral carbons, but it is having an internal plane of symmetry. It is having an internal plane of symmetry. Therefore, this molecule is optically inactive. Why? The right rotation of the upper half is we can say compensated by the left rotation of the lower half. This is the simplest way of putting it. And therefore, this also is optically inactive. This is also optically inactive. Now we have already mentioned that the Fisher projection. See what is the actual structure of this molecule. See, for example, I write COH here. Let me go here. OH, H, CS2OH. Now, when we draw this, we should remember that these two bonds are projecting towards you. This is the actual structure. Okay, Liana. What is that? Liana. Something is wrong. No. Okay, COOH. What happened, Liana? You have some problem? Some message from you? No? Okay. Now, here is no message. Okay. Now see here. COOH, CS2OH. So this is the actual structure of this molecule. Now, while keeping this in your mind, we will draw this same structure here for this molecule. Remember, we are trying to draw the actual structure of this molecule and find out the relationship here. So this is, see here very carefully. OH, H, OH, H. This is the actual form of the molecule. This is the same as this, remember that. That is, when we draw this structure, we should remember it is having this structure. Now let us do one thing. We will just rotate this molecule along the vertical line. Okay, rotate it 180 degrees. Rotate this 180 degrees. Now, what will happen? The back group will come to the front. Look very carefully. COOH. C, sorry, I don't want to write that. And this group also will come to the front. Now the groups in the front will go to the back side and OH will come here. Remember that. So here OH and here H. Understand this very carefully. What we are doing. Oh, sorry. Every chance of committing mistakes in stereochemistry. Okay. So these two are the same. Remember, we have only rotated the molecule. We have not broken any bond. When you don't break the bond, you are not making the making a different molecule. The molecule remains the same. We are just rotating these molecules in different ways. Now let us rotate this molecule again along this axis, along the horizontal axis. Okay, 180 degrees. Rotate along this axis 180 degrees. Okay, what will happen? This group will come to the top. This COH will come to the top. And this COH will come down here. But remember, it is again COH only. And the bond in the front will go to the back. See this. Whatever bond is here will go to the back side. Whatever bond is to the front will go to the back side. So it will again get reversed. And this, look at this hydrogen, this will come here. And this will come here. Same is the case with OH. So we can draw H here, OH here, H here, OH here, and COOH here. COOH. Okay, now look here. What is the actual structure of this molecule? Yeah, now this is in a Fischer projection writable form. You can draw, this is actually a Fischer projection. See this? COOH, H, OH, H, OH, and COOH. And compare this and this. They are identical. That is, these two are identical, not enantiomers. Why? Because they have an internal plane of symmetry. And the one which is having an internal plane of symmetry is known as not as enantiomer, but mesocomplex. And therefore, these two are just the same. So only you don't have 4 forms, you have only 3 forms. Is that clear? This is the concept of mesocomplex. Okay, right. Suppose you are given you are given 2 samples. Remember, mesocompound is a single compound. This you are saying. You are given 2 samples. You are asked to find out which is mesocompound, which is a DL mixture. Suppose you are given 2 samples of nitric acid. One contains a mixture of these two. Sorry, not these two. These two. They are enantiomers. An equal mixture of these two. That is what is called a DL mixture. And you are given another one, you are given this compound. So one of them is meso and the other is DL. How will you identify them? Simple way, you subject both the samples to resolution. We are come to resolution. That is, try to resolve both of them into enantiomers. One of them you can resolve into two forms, a plus and minus. The other one, whatever you try, you cannot separate into two. The one which is non-separable into enantiomers will be a meso compound. The one which can be separated into two optically active enantiomers, that will be DL mixture. So DL mixture is separable because it's a mixture. Meso compound is non-separable because it is not a mixture. Simple. Okay. So this is about meso compound. Now, let us very briefly tell you what is racemization and resolution. Racemization is conversion of an optically active compound into an optically inactive equal mixture of uh, enantiomers. Okay, so that is racemization. Suppose you treat, I clear the board. Suppose you take lactic acid. Lactic acid is CH3 OH HCO. Okay. Now, if you put a little base into lactic acid, if you put a little base into lactic acid, it can easily undergo tautomerization. It can easily undergo tautomerization. What actually happens? This OH will capture this photon, and you have a, I just COOH. So you will have an enol. Okay. Now, when you reprotonate this, the same water molecule which has come out from here, HOH. Okay. Now this can come back, and this can be protonated either on this side or on this side, and OH can come this side. So in fact, you will get a mixture of HOH plus OH. You'll get a mixture of these two. Okay. So treatment of a base will tautomerize and will form the DL mixture. And equal possibility. On this side, there is equal possibility of protonating. This is what is called racemization. This is great application in industry because you can unwanted enantiomers can be converted into DL mixer and then separate them and get more and more of the right required products. Okay. All these things I have described in detail during the class. Next is resolution. Separation of racemic mixture into individual, opposite of racemization. Separation of racemic mixture into enantiomer D and L enantiomers. Racemic mixture into enantiomers. There are different methods which we have described. One, mechanical separation. Mechanical separation. What is a typical example for this? Yeah. Sodium ammonium tartrate. Sodium ammonium tartrate. Sodium ammonium tartrate. See, tartric acid we have just now seen. CO minus. So sodium ammonium means one of them is sodium and the other is ammonium. NH4 plus. This salt can be separated. Remember, it is D and L mixture, not meso. So you have to write this structure. Don't forget it. Don't put the OH group on the same side. Now, so this there is a beautiful feature for this. The crystals formed from these compounds is also having a mirror image form, just like the structure we draw. The crystal also, if it is forming something like this, you keep a mirror in front of one of the crystal. You can see that I cannot draw it. You can see that some crystals should be just having the same shape in the opposite direction. You can see the mirror images. So what you can do is you can just pick them up by looking with your eye or through microscope. And this is how we do it. First separated the enantiomers. Okay, but remember this is very rare to happen. By luck only Pasteur have got it. I don't know anybody else could do it. I don't know. I have not come across any other example. If you ask me, sir, give us another example, I don't have it. I have not come across. So it is not having any importance because it cannot be used in industry. Nobody can pick it up and industrially use it. The second method is biochemical separation. Second, biochemical. What is biochemical separation? Okay, again, it is real tartaric acid was the victim of this also. Real tartaric acid. There are certain microorganisms which can eat. I will use the word eat. Actually, you can say destroy. Destroy specifically one enantiomer, keeping the second one intact. That is biochemical separation. But remember, this is also very rare. Very, very rare. You have to get the right microorganism for it. That is one thing. Second thing, half of the material is eaten by this fellow, right? So you are wasting half. So that is also not okay. And there are certain cases in which the enantiomers are poisonous to the microorganism. Enantiomers will be poisonous to the microorganism. So you cannot use this method for such enantiomers. So that is the second. The third one is what is called chemical method. Chemical method. Okay. What is the underlying principle? Enantiomers cannot be separated. That is the underlying principle. Enantiomers does not differ in normal physical and chemical properties. Differ, we'll just talk about physical only. In physical properties. What are the physical properties? Melting point, solubility, boiling point, all this stuff. Especially the solubility. That is the most important thing. Because solubility is something related with crystallization. Crystallization is the process of purification of compounds. So, enantiomers does not have these differences. But we have observed diastereomers. Diastereomers, which just now we have seen in the case of tartaric acid. The diastereomers differ in their physical and chemical properties. Differ in the physical and chemical properties. Okay. Based on these observations, what we can do is convert enantiomers into temporarily into diastereomer. Okay. What we have to do is introduce one more asymmetric carbon into the molecule by a chemical reaction. It becomes diastereomer. So you take a mixture of D and L. You take a mixture of DL mixture, react it with an optically active compound. React with an optically active compound. Optically active means it will be having only D or L. So we will put D only. You will get a product in which there is D of this and D of this reacted together. So this is one product. And then L of this and D of this. So these will be the two products obtained. They will be having different solubility. So remember, this is obtained in a mixture. Now your job is to separate them. Separate them by crystallization. Separate them by crystallization. So when you separate them by crystallization, you'll get DD inside here and DL here. Okay. Now bring them back. Find an easy method to convert this DD into back into the starting D and this back into N. This is the basic principle behind the resolution process, chemical resolution. Okay, I have to write chemical. I will written chemical resolution. Let me give you an example for this. That is important. So we have TL lactic acid again. You take the mixture, DL mixture, and into that you add an optically active compound known as L-bromine. It's a natural product. L-bromine. You'll get L-bromine D-lactate. Remember, brucine is an amine, a base, and lactic acid is an acid. Acid and base will react to form salt. So we will get the salt L-brucine D-lactate, and L-brucine, remember it is again L only, L-lactate. Now look at this. This is a single compound, this is a single compound, this is another single compound. So we get a mixture in a beaker. Okay, this is totally in a beaker. Now see here it is identical, both are L. On the other part you have one L and one D, therefore they are not mirror images. So non-superimposable. They are stereoisomers, so they are stereomers. Now separate them into L-brucine, D-lactate, L-brucine, L-lactate. So you have separated them. Then you take them separately and add HCl. You will get lactic acid separate. Is that clear? In each case, you will get lactic acid. From the first, you will get D-lactic acid. From the second, you will get L-lactic acid. Next method is absorption method, selective absorption method. Okay. There are certain chromatographic columns, column materials, like starch, cellulose, quartz. Starch, cellulose, they are all optically active. They are called optically active column. So run an optically active column chromatography, which contain some materials which are optically active, starch, cellulose, etc. Okay, and you can separate them. For example, you can separate camphor into D and L form by using D-lactose as the adsorbent. D-lactose. Camphor can be separated. Camphor separated by D-lactose as adsorbent. What's the meaning? You take a burette or a column in which you add D-lactose, then take the racemic mixture of the camphor, load on the column, and do a column chromatography. The two components will be separated. You can collect them. Okay, so this Now in this one, in the serial chemistry, the last part is configuration, absolute configuration. Okay, they are kept as last part. That is R and S. Say whether which is R or S. Now let us take first the Fisher projection and find out. I have CS3 here, H here. I will put the COH here first. You can put it anywhere, of course. Now what is the configuration of this? The method I have given the number wise, I have mentioned in the class. Number 1, identify the chiral carbon. You know what is a chiral carbon. Ensure that there is a carbon which contains all the 4 different atoms and groups are different. All 4 atoms and groups are different. So identify the chiral carbon. Second step, identify 4 different atoms and groups. Number 3, give priorities by CIP rule. Give priorities by CIP rule. And number 4, bring the least priority group away from the observer. This is what everyone forgets. Least priority, most away. Least priority group, most away.